Annenberg Media.
Throughout history, mountains have been deeply embedded in the human experience. We've worshipped them, created nations using them as boundaries, stripped them of valuable resources, and returned to them for inspiration and recreation. If you are at all curious about the Earth, you've probably wondered why mountains exist. This question has intrigued Earth scientists ever since the emergence of geology as a science in the late 18th century. And the more we learn about mountains and what they're made of, the more fascinating this question becomes. Most mountains are forming today in tectonically active regions, where the movements of plates deform the rocks of the Earth's lithosphere. The tremendous energy that's expended in the mountain building process often has a profound effect on these rocks. The geologic events that accompany mountain building, such as the collisions between plates, deep subsidence of portions of the Earth's crust, moving masses of magma, and the displacement of rock bodies along fault zones focus heat and pressure on the rocks. As a result, these rocks are changed dramatically. This process of change by the effects of heat and pressure is called metamorphism, a term derived from the Greek words meta, which means change, and morph, meaning form. Metamorphism changes the appearance of rocks, their mineral composition, and even their age, as measured by radiometric dating. During metamorphism, atoms within the rock can dislodge themselves from mineral lattices and move about freely. This atomic reshuffling causes existing minerals to recrystallize and new minerals to form. This process also resets the radioactive clock within the rock to the time of metamorphism. Metamorphism can result in complex structures and rare minerals that make these some of the most bizarre-looking and strikingly beautiful of all crustal rocks. But to a geologist, the real beauty of metamorphic rocks is the information they contain about tectonic processes and Earth history.
Metamorphic rocks can appear in many forms. From platy, black, fine-grained stone, to granite-like layered rock, to the marble used by sculptors. One explanation why a wide variety of metamorphic rocks exists is simply that there are many different sedimentary and igneous rocks, each responding to metamorphic conditions in its own unique way. Geologists use the term protolith to refer to the original rock existing before metamorphism. For example, limestone is the protolith of marble, one of the most common metamorphic rocks. And basalt, a volcanic igneous rock, is the protolith of amphibolite. But geologists have found many more types of metamorphic rocks than protoliths. So factors other than original composition must also play a role in creating these rocks. Study of geologic structures such as folds and faults suggests that there is a wide range of pressures and temperatures inside growing mountain belts. Quite likely, this plays a critical role in explaining variations in metamorphic rocks. Laboratory experiments have helped geologists understand metamorphic conditions.
The conditions under which metamorphism occurs is beneath the level of weathering and sedimentation to form the sedimentary rocks, generally at temperatures of a greater than 200 degrees, and at conditions that do not produce a melt such as goes into igneous rocks. So the the range in temperatures are roughly about 200 degrees C to about 800 degrees C. The process and the formation of the rocks occur at depths generally from 2 to several tens of kilometers in depth beneath the Earth's surface.
At the surface, we are accustomed to the pressure of the air surrounding us. We don't notice the air because the pressure is equal all over our bodies. Deep underground, however, pressure is not equally applied. Rock can be squeezed strongly with pressure greatest in the direction of the squeezing. Sometimes, opposing pressure can be applied on different parts of a rock, causing it to bend or shear apart like a sliding deck of cards. Whether from shearing or simple squeezing, the rock is experiencing what geologists refer to as directed pressure or directed stress. The structure of many metamorphic rocks is a result of directed pressure. Directed shear stress, for example, helps explain the origin of a spectacular form of crystal growth. These swirling images suggest several things: a cluster of spiral galaxies, the Chinese symbol for yin and yang. They are, in fact, snowball garnets. To the geologist, frozen slices of metamorphism in action. The swirling pattern in a snowball garnet is formed by planes of tiny mineral inclusions that are swallowed up by the garnet as it grows. Shear stress causes the garnet to rotate during growth, distorting the planes into swirls. The three-dimensional form of the swirling pattern can be shown by means of a multi-ringed model. Each ring represents the edge of a plane of minerals incorporated by the growing garnet.
These are the rings. And let's do that process as it goes on so we can visualize it. First we grow a little bit of garnet, then we rotate the ring, we rotate that and grow another ring and rotate it with the ring inside, and we grow another ring and so forth until we develop basically a shape like this, in which we have a little pit over here and a little mound over here and the diameter of the rotation here. We can compare that with a real specimen, which is over here, and this is a real specimen in which we see the little pit here, the little mound here, the common axis through here, and it shows the snowball pattern. In the same specimen, we can see a cross-section of a garnet that's grown considerably more than that garnet has, showing that rotation.
Directed stress involving compression helps explain the origin of a very common metamorphic structure. As temperature and pressure increase, minerals recombine to make new, more stable minerals. The minerals grow in the directions of lowest pressure, perpendicular to the directed stress. This results in a layering which geologists call foliation. Shear stress, too, can cause foliation.
I'll hold a piece of a metamorphic rock we call a schist, a mica schist, and we can see it's very layered. That layering is a preservation of a stress field generated within a subduction zone environment. As the rock is recrystallized under great pressure and great temperature, it is also recording in it the intensity of the stress field. We see stresses that had to be in some sort of direction to planarize the micas, forming the mica schist.
Foliated rocks are easy enough to spot, but are often taken for granted at some cost. Constructing roads, dams, or foundations on such rocks can create severe problems.
The production of foliation within metamorphic rocks gives rise to the same type of structural heterogeneity and weak directions as you find within landslide-prone, for instance, sedimentary rocks. So although we consider these basement rocks to be quite stable, in reality schist can be very unstable. Any engineering firms that were wanting to construct either houses or dams or other type of constructions on metamorphic rocks has to take into consideration the foliation and the direction of the foliation to make sure that it isn't in an unstable orientation with regards to any engineered works that could be constructed on it.
We've done a stability analysis.
In addition to directed stress, rising temperature will cause minerals in a metamorphic rock to react, forming new crystal lattices and mineral types. This process, called recrystallization, generally causes minerals to grow larger, developing an interlocking texture resembling that of igneous rocks. For example, when the sedimentary rock limestone is metamorphosed by heat into marble, the fine grains of calcite in the original limestone recrystallize into large calcite crystals, which interlock to give the emerging marble a coarse texture. In some circumstances, the temperature of a deeply buried rock can become so great the rock starts melting. When this happens, a rock having both igneous and metamorphic features results. Geologists call these intermediate rock types migmatites, or mixed rocks. In some migmatites, geologists find evidence for the origin of one of Earth's most common igneous rocks, granite. Yet another factor may be critical in creating metamorphic rocks. For many years, geologists believed that the overall composition of a rock rarely changes during metamorphism. However, this is no longer assumed to be the case.
The other aspect of metamorphism as a result of these metamorphic reactions is that the rocks undergo changes in composition. And mainly, this shows up in the formation of the liberation of H2O and its departure from the rocks. So the rocks dry out in very much the same way that a fired pot dehydrates in a kiln. The main feature of higher temperatures, for example, is to cause the rock to undergo loss of certain volatile components. And in most metamorphic rocks, that means mainly the loss of H2O and CO2.
Fluids are released not only by metamorphic rocks at high temperatures, but from magmas intruding the metamorphic rocks as well. During mountain building, the crust in many places is saturated with migrating fluids. These accelerate some chemical reactions and may stop others. So, the spectacular diversity of metamorphic rocks is created by the numerous protoliths, the presence of fluid, and the wide range of temperatures and pressures possible within the Earth.
When rocks are exposed to the heat and pressure of metamorphism, they undergo changes both in texture and mineral content. The specific changes that take place depend on a variety of factors, including the composition of the original rock, called the protolith, how much heat and pressure are applied, the length of time of metamorphism, and whether or not water is present. Most metamorphic rocks form in one of two geologic settings. The first is where cold rock is intruded by a hot magma. This is called contact metamorphism, and its effects are confined to a small area. The other setting is at a convergent plate margin, where the motions of the plates generates metamorphic conditions over a wide area, in places covering thousands of square kilometers. This is known as regional metamorphism.
One of the main differences between contact and regional metamorphism is that temperature is the predominant cause of contact metamorphism, whereas regional metamorphism involves both temperature and pressure.
The chemical changes that accompany contact metamorphism, especially of marbles, is seen on this hand-sized sample of a contact. On the left side is an intrusive igneous rock, a tonalite, that came into contact with a limestone. The limestone was heated up, and at the same time it was heated up, that there were elements that left, both chemical elements that left the intrusive rock into the marble, and then elements that left the marble and went into the intrusive rock. The material leaving the intrusive rock consisted of some iron, aluminum, and silicon, which went to form garnets, the brown material here. Silica continued in further into the marble than did the other two elements and resulted in the formation of a layer of the mineral wollastonite, which is a calcium silicate. This is a good example of a well-layered rock produced by regional metamorphism in the so-called amphibolite facies. It consists of alternating layers, the light of quartzite and of dark mica schist bearing the aluminum silicate mineral sillimanite. At first that you would think these are relic sedimentary beds, but they are not. They've been structurally transposed from sedimentary beds into tectonically bounded layers. Here you can see two of the biotite-rich layers coming together to constitute a single layer. So there has been a great deal of directed shear or pressure through this rock that has produced this well-layered aspect to it.
Metamorphism has been compared to cooking. The dish that you wind up with depends both on your starting ingredients and on the way you cook them. Likewise, laboratory experiments have shown that the composition of rocks changes very little during metamorphism. But as temperature and pressure increase, the atoms within the rock become mobile and recombine to form new minerals. These experiments have also shown that the various metamorphic minerals, or assemblages of minerals found together, form only within specific ranges of temperature and pressure. So geologists can use minerals in metamorphic rocks as pressure gauges and thermometers to understand the conditions under which metamorphism took place. This chart is an example of how minerals are used to interpret the metamorphism of basalt, the rock that makes up the crust of the world's ocean basins. Pressure on the chart increases downward, and temperature increases to the right. This is a piece of unmetamorphosed basalt which formed at the Earth's surface. This rock would plot here on our chart at relatively low temperature and pressure. As basalt is metamorphosed to different combinations of temperature and pressure, its mineral composition changes as the rock re-equilibrates to its new conditions. These zones on the chart are called metamorphic facies, and each facies is defined by the formation during metamorphism of a particular mineral or mineral assemblage. For example, this is a metamorphosed basalt containing the mineral amphibole. Amphibole forms at a temperature between 450 and 700 degrees centigrade and at a pressure corresponding to a depth of at least 6 kilometers. So this metamorphosed basalt would plot here on the chart in the amphibolite facies. This is a metamorphosed basalt that contains zeolites, another mineral group, and it plots here in the zeolite facies. The zeolite facies corresponds to less intense metamorphic conditions than does the amphibolite facies, so rocks containing zeolites are said to be of lower metamorphic grade. Metamorphism is a process of progressive change. As rocks are exposed to higher and higher temperatures and pressures, they are altered in a predictable manner. As the intensity of metamorphism increases, the rocks become harder and more coarsely crystalline and develop special metamorphic textures. Geologists refer to progressive metamorphism as an increase in metamorphic grade from low to high. And the best way to see this pattern of change is to begin with an unmetamorphosed protolith and watch it change as the intensity of metamorphism increases.
Geologists can see how particular rock types undergo progressive metamorphism by tracing widespread rock formations from areas where no metamorphism has occurred into areas where metamorphism is extreme.
If our starting material is like a claystone like this, a sedimentary rock, relatively aluminous rich, on heating this under the low part of the regional metamorphism, that we develop a very layered, finely layered rock called a slate. That it doesn't have any recognizable minerals in it because they have not grown large enough. But due to the growth of new minerals and of the directed pressure, that we end up with a very well foliated rock it's possible to cleave into very regular thin layers. With increased temperature and pressure, that the slate then is transformed into a slightly higher grade rock, which is called a phyllite. This rock has a linear structure to it as well as to the foliated structure, and it is a little slightly different in luster due to the larger mica-sized crystals. As the temperature and pressure increase further, that we develop a schist. In this case, this is a garnet schist with large garnet crystals, lots of white mica, very coarse crystals. This would be formed at quite high metamorphic grade. At yet higher metamorphic grade, that you constitute a gneiss, where that you start having minerals segregate into definite layers.
If metamorphic rocks form inside the Earth as temperatures and pressures rise, why aren't they unmetamorphosed as temperatures and pressures fall back down? In part, this is because loss of fluids during metamorphism makes it impossible for certain chemical reactions to reverse themselves. Also, as temperatures drop, ions cannot migrate easily through the rock, so minerals will not recrystallize. So in most metamorphic rocks, geologists find a preserved record of the greatest temperatures and pressures occurring during crustal deformation. With the development of plate tectonics theory, the temperature and pressure changes geologists have long seen in metamorphic rocks finally began to make sense.
For many years, geologists had been able to relate individual facies to the pressure and temperature conditions of metamorphism, but they had no satisfactory explanation for the geologic processes that form metamorphic rocks. That is, until the theory of plate tectonics emerged. One good example is this relatively rare metamorphic rock called blue schist. Experimental work had shown that the minerals in blue schist form only under very unusual metamorphic conditions. These conditions are a pressure range equivalent to a depth of 15 to 30 kilometers in the crust and a very cool temperature, only 200 to 400 degrees centigrade. That's the approximate cooking temperature of a kitchen oven or toaster. At a depth of 15 to 30 kilometers, however, the temperature is normally about twice as hot, 500 to 750 degrees centigrade. So the only way that rocks can be metamorphosed to blue schist facies is to be quickly shoved down to those extreme depths and then rapidly brought back up before the rocks have time to heat up completely. And that's exactly what happens where two tectonic plates are colliding in a subduction zone. In fact, blue schist-bearing rocks normally occur in long linear zones that mark ancient plate subduction boundaries.
Metamorphic rocks provide geologists with the most complete picture of temperatures and pressures developed when plates collide. In addition, these rocks contain other fundamental information. In the metamorphic regions of the northeastern United States, for example, snowball garnets preserve an important record of the building of the Appalachian Mountains. By comparing the amount of rubidium isotope decay at the center of these garnets relative to their margins, geologists can determine how fast the crystals grow.
The garnets in Vermont took about 10.5 million years to grow, and this corresponded to a growth rate of roughly a few atomic diameters per year. And to give you some comparison of what that might be in terms that might be more in a human reference frame, that corresponds to about a millionth as fast as the diameter of an ordinary tree might grow. So it's in a very slow process.
The Vermont garnets began growing about 380 million years ago, as the continents of Eurasia and Africa drifted toward the Americas to form the supercontinent of Pangaea. The convergence of the plates gradually heaved up the rocks of northeastern North America to create the Appalachian Mountain Range, pushing the rocks into huge, flat-lying folds called nappes. Buried deep inside these giant folds of rock tiny garnet crystals echo the twisting and contorting going on around them, rotating and spiraling between 20 and 30 degrees every million years.
The beauty about the garnets in Vermont is that these are, the ones we measured were snowball garnets. And so we get some other useful information from the garnets studied in Vermont. That information tells us how fast the rocks were deforming. In other words, how fast the garnets were rotating. That tells us how fast the rocks in the surroundings around the garnets were causing that rotation, were deforming. And that is something that has never been measured before. It's a considerable interest for people studying tectonism, because we're actually measuring the rates at which the rocks get folded. And that's what another factor we're interested in.
Like a tiny black box flight recorder in an airplane, or a trip odometer in a car, a snowball garnet provides geologists with a crystalline log of plate collision and mountain building spanning millions of years.
Metamorphism is a fundamental rock-forming process on Earth. About 15% of all continental crust exposed at the surface is composed of metamorphic rocks, and much of the oceanic crust is metamorphosed to a low grade as it forms. Just as fossils are a record of life through time, metamorphic rocks are used to study the history of the Earth. They allow us to reconstruct the movements of plates that no longer exist, and to study mountain ranges that have long since worn away. Like the opening of new oceans, the movement of continents, and the creation of mountain ranges, metamorphism is a consequence of plate tectonics. The rise in temperature and pressure that makes metamorphism possible is almost always linked to plate movement and mountain building. The collisions and intrusions and fault zones that metamorphose the rocks are concentrated at plate margins. As rocks are depressed to great depth, say tens of kilometers in a subduction zone, or placed under the great compression of a continental collision, metamorphic conditions can become so intense that the rocks begin to melt. The magma rises buoyantly toward the surface, setting the stage for the formation of new rocks and new metamorphic transformations. When we study metamorphic rocks, we're seeing a brief glimpse of this cycle of rock formation and change, a cycle that's as old as the Earth itself.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.